Welcome to this coding walkthrough. Today, we'll be tackling LeetCode problem number 230, kth smallest element in a BST. This is a fascinating problem that challenges us to efficiently find the kth smallest element in a binary search tree, leveraging properties of BSTs. Whether you're preparing for interviews or brushing up on your algorithms, this problem is a great opportunity to strengthen your understanding of tree traversal techniques. Let's dive in. In this problem, you are tasked with finding the kth smallest element in a binary search tree, or BST. A BST is a special kind of binary tree where each node satisfies two key properties. First, all the nodes in the left subtree of a node have values smaller than the node itself. Second, all the nodes in the right subtree have values greater than the node. This structure ensures that an in-order traversal of the tree will produce the values in sorted order. You are given the root of this BST, along with an integer k, which tells you the rank of the smallest element to find. It's also guaranteed that the BST will have exactly k elements that satisfy the conditions, so you don't need to worry about edge cases where k is out of range. The input consists of the root node of the BST and the integer k, and the output will be a single integer representing the kth smallest element in the tree. Now, let's look at an example to clarify the problem. Suppose the input is a binary search tree where the root node has the value 3, with 1 and 4 as its left and right children, respectively. The left child, 1, also has a right child with the value 2. The BST structure is shown here. For this tree, if k is 1, we're looking for the smallest element in the BST. By performing an in-order traversal, which visits nodes in sorted order, we get the sequence 1, 2, 3, 4. The first element in this sequence is 1, so the output is 1. This example illustrates how the in-order traversal is key to solving the problem. Let's consider another example. Here, the input BST has the root node 5, with 3 and 6 as its left and right children. The left child, 3, further has two children, 2 as its left child and 4 as its right child. The node 2 also has a left child, 1. The tree structure is provided here. If k is 3, we're looking for the third smallest element. Performing an in-order traversal of this BST produces the sorted sequence 1, 2, 3, 4, 5, 6. The third element in this sequence is 3, so the output is 3. To further solidify the concept, let's look at another example. In this case, the BST contains only one node with the value 1. Since there's just one node, the in-order traversal simply results in 1. If k is 1, we're asked for the smallest element, which is the first and only element in this case 1. The output is therefore 1. This demonstrates that even for very small trees, the approach to solving the problem remains consistent, relying on the in-order traversal to find the kth smallest element. Now let's discuss the constraints and edge cases for this problem. The number of nodes in the tree can range from 1 to 10,000, meaning the tree can be very small or quite large. Node values are guaranteed to be unique and will always fall between 0 and 10,000. Additionally, the value of k will always be between 1 and the total number of nodes in the BST, so you don't need to handle invalid k values. Some edge cases to consider include a tree with only one node, where the kth smallest element is simply the root value. For a balanced tree, the kth smallest element will depend on its position in the sorted order of an in-order traversal. In a skewed tree, where all nodes are either left or right children, the traversal will look like a sorted linked list, and the kth smallest element will correspond directly to the kth node in that traversal. To solve the problem of finding the kth smallest element in a binary search tree, we need to consider approaches that leverage the properties of a BST efficiently. One straightforward method is the brute force approach using an in-order traversal. The intuition here is that an in-order traversal of a BST naturally produces a sorted sequence of its elements. By performing the traversal, we can collect all the values in an array. Once we have this sorted array, we can directly access the k1 indexed element, which corresponds to the kth smallest number. However, while this method is simple and intuitive, it has notable drawbacks. It requires traversing all nodes to build the array, which takes n time, and storing all elements in the array consumes n space, making it inefficient for large trees with many nodes. The brute force approach, though easy to understand, is not optimal because it uses extra space for the array and does not allow early termination once the kth smallest element is identified. This leads us to a more optimized solution, performing an innerder traversal with an early stopping mechanism. The key idea here is to avoid storing all elements and instead count nodes directly during the traversal. Since the innerder traversal inherently visits nodes in sorted order, we can stop as soon as we've visited the kth node. To achieve this, we maintain a counter that tracks the number of nodes processed. When this counter matches k, we record the current node's value and terminate the traversal. This approach is more efficient in practice, as it eliminates unnecessary computation. The time complexity is O, h plus k, where h is the height of the tree, and the space complexity is O, h, due to the recursion stack. This makes it especially well suited for larger trees, as it reduces both time and space overhead. To further improve upon the recursive approach, we can use an iterative version of the innerder traversal. This eliminates the need for recursion and uses an explicit stack instead. The iterative process involves pushing all left nodes onto the stack until the leftmost node is reached. Then, we pop nodes from the stack, increment a counter, and check if the counter matches k. If it does, we return the value of the current node. This approach shares the same time complexity of O, h plus k, and space complexity of O, h, as the recursive method, but it avoids the limitations of recursion, such as potential stack overflow in deep trees. The iterative approach is especially useful in environments where minimizing recursion depth is a priority, though it does come with slightly more complex implementation compared to its recursive counterpart. After evaluating these approaches, the optimized innerder traversal with early stopping emerges as the most efficient and intuitive solution for this problem. This method leverages the sorted order of BST elements to minimize unnecessary computation. Its early termination mechanism ensures that we traverse only as much of the tree as needed, which is particularly important when k is large and the tree is balanced. While the iterative approach shares similar time and space complexity, we prefer the recursive version for its cleaner and more readable implementation. However, it's important to note the trade-offs. The recursive method uses implicit stack space, whereas the iterative version explicitly manages the stack, making it more memory efficient. The brute force approach, on the other hand, is simple but inefficient in both time and space. Ultimately, the chosen strategy strikes the right balance between simplicity, efficiency, and clarity, making it the ideal solution for this problem. The problem we're solving here is LeetCode number 230, which asks us to find the kth smallest element in a binary search tree, or BST. A BST is a special type of binary tree where, for any given node, all values in the left subtree are smaller, and all values in the right subtree are larger. This unique property makes it an ideal structure for problems involving sorted order. To solve this problem, we use an approach called innerder traversal with early stopping. The intuition behind this approach is that an innerder traversal of a BST naturally visits the nodes in ascending order. By performing this traversal, we can track how many nodes we've visited and stop as soon as we reach the kth smallest element. The algorithm has a few key steps. First, we define a recursive function innerder node that handles the traversal. This function uses a counter to track the number of visited nodes and a variable to store the kth smallest element once it's found. Second, we include a base case to immediately return when we encounter a null node, ensuring the traversal works seamlessly at leaf nodes and doesn't go out of bounds. These foundational steps set the stage for the core logic of the algorithm. The next step in the algorithm is the recursive logic of the innerder traversal itself. With the BST's sorted nature, we start by traversing the left subtree, which contains all smaller elements. Once we reach a node, we increment our counter to reflect that we've visited it. At this point, we check if the counter equals k. If it does, it means we've found the kth smallest element, so we store the current node's value in our result variable and stop further traversal. This is what we call early stopping, a key optimization in this algorithm. If the kth smallest element hasn't been found yet, we proceed to the right subtree, which contains all larger elements. To tie everything together, we use a driver function. This initializes the counter and result storage at the start, then calls the innerder function on the root node of the BST. Once the traversal completes, the driver function simply returns the stored result. The key insight here is how the innerorder traversal leverages the BST's properties to efficiently visit nodes in sorted order, while early stopping ensures we don't waste time visiting unnecessary nodes. The early stopping mechanism is particularly useful for large BSTs with many nodes, as it prevents unnecessary computation. This optimization is important because, in some cases, we might find the kth smallest element long before we've traversed the entire tree. In terms of space efficiency, the algorithm requires O(h) space, where h is the height of the tree. For a balanced BST, this is O log n, which is very efficient. However, for a skewed BST, where all nodes are on one side, the space complexity could degrade to O(n). As for time complexity, the algorithm visits only the nodes needed to find the kth smallest element. In the worst case, where k equals the total number of nodes, we would visit every node, resulting in O(n) time complexity. For smaller values of k, the traversal may end much earlier, which can significantly reduce the number of nodes visited. The algorithm leverages two key data structures, the BST itself, which ensures the innerorder traversal produces a sorted sequence, and simple variables like the counter and result storage. These ensure the implementation remains lightweight and focused. Here is the Python implementation of the algorithm. We define a class solution with a method kth_smallest that takes the root of the BST and the value k as inputs. Inside this method, we initialize two variables, self.count to keep track of the number of nodes visited so far, and self.result to store the kth smallest element once it's found. The core of the algorithm is the recursive innerorder function. The first thing this function does is check if the current node is null or if the result has already been found. If either condition is true, it simply returns. Otherwise, the function recursively traverses the left subtree, ensuring that smaller elements are visited first. When visiting the current node, it increments the counter and checks if the counter equals k. If it does, the node's value is stored in self.result, and we return immediately to prevent further traversal. Finally, if the kth smallest element hasn't been found yet, the function proceeds to traverse the right subtree. The traversal starts with a call to innerorder on the root node, and once it finishes, the result is returned. This implementation is both concise and efficient, making it well suited for solving the problem. Now let's address some edge cases and key optimizations for this algorithm. For an empty tree, where the input root is null, the function should handle this gracefully without errors. When k equals 1, the algorithm should correctly return the smallest element in the BST, which is the first element visited during the innerorder traversal. Similarly, when k equals n, where n is the total number of nodes, the algorithm should return the largest element in the BST, as this is the last element visited in sorted order. If k is invalid, such as being less than 1 or greater than n, the function's behavior is undefined, but we assume k is valid as per the problem constraints. One key optimization in this approach is avoiding a full traversal of the tree. By stopping as soon as the kth smallest element is found, we significantly reduce the number of nodes visited, especially for small values of k. While the recursive implementation is elegant, it does use stack space proportional to the height of the tree. For very large or skewed trees, an iterative approach with an explicit stack can be used to prevent potential stack overflow issues. These considerations ensure the algorithm is robust and efficient for a wide range of inputs. This implementation solves the problem of finding the kth smallest element in a binary search tree, BST, using the innerorder traversal approach. Here's a breakdown of the code. 1. TreeNode class. This is the standard definition of a tree node in a binary tree. Each node has a value, val, a left child, left, and a right child, right. 2. Solution class in kth_smallest method. The kth_smallest method belongs to the solution class and takes two inputs, the root of the BST, root, and the integer k. 3. Innerorder traversal helper function. The innerorder function performs a recursive traversal of the BST. The innerorder traversal sequence visits nodes in sorted order for a BST. The recursion works as follows. For a given node, it first recursively traverses the left subtree, innerorder node.left. Then, it includes the current node's value, node.val. Finally, it recursively traverses the right subtree, innerorder node.right. For combining results, the innerorder function returns a list of values from the left subtree, appends the current node's value, and then adds the values from the right subtree. This results in a fully sorted list of all elements in the BST. 5. Accessing the kth element. After the traversal, sorted underscore elements contains all the BST values in sorted order. Since k is 1 based, we return sorted underscore elements, k1, to get the kth smallest element. ### complexity analysis. Time complexity. The inner traversal visits each node exactly once, so the time complexity is O(n), where n is the number of nodes in the BST. Space complexity. The recursion stack and the sorted underscore elements list both require O(n) space. This solution is simple and leverages the inherent sorted property of BSTs through inner traversal, making it easy to understand and implement. Here, we start with the definition of a tree node class to represent nodes in a binary search tree. Each node contains an integer value, along with references to its left and right child nodes. Following that, we define the solution class, which contains the method kth_smallest. This method takes the root of the binary search tree and an integer k as inputs. The goal is to find the kth smallest element in the tree. To achieve this, we create a list called sorted elements to store the values of the tree nodes in sorted order. We then perform an in-order traversal of the tree, which naturally visits the nodes in ascending order for a BST. After populating the list, we retrieve the k1th element, as lists in Java are 0-based, but k is 1-based, hence the adjustment. The in-order traversal method is defined to handle the in-order traversal of the tree. This method takes a tree node and a list as inputs. The base case checks if the current node is null. If so, we simply return, as there are no further nodes to process. For non-null nodes, we first recursively traverse the left subtree, which ensures that smaller values are visited first. Then, we add the value of the current node to the sorted elements list. Finally, we recursively traverse the right subtree to process the larger values. This traversal guarantees that the elements are added to the list in ascending order, enabling us to easily retrieve the kth smallest element. In this example, we are tasked with finding the second smallest element in the given binary search tree. The tree has a root node with a value of 3, and it has 2 children, 1 on the left and 4 on the right. Node 1 also has a right child, which is 2. To solve this, we start by calling the function kth_smallest with the root node, which is 3, and k equals 2. To determine the kth smallest element, we use an in-order traversal because it provides the elements of a BST in sorted order. Starting at the root, we recursively traverse the left subtree first. For node 3, this means we call in-order 1. At node 1, we again traverse its left subtree, but since it's none, it returns an empty list. We then visit node 1 and add it to our result. Next, we move to the right subtree of node 1, which leads us to node 2. For node 2, we first traverse its left subtree, but since it's also none, it returns an empty list again. Now at node 2, we visit it and add it to our result. Afterward, we traverse its right subtree, which is also none, returning an empty list. Combining these results, we have 2 from node 2. Going back up to node 1, we combine the left subtree result, which was empty, the value 1, and the right subtree result, 2, to get 1, 2. Returning to node 3, we now visit it and add its value, resulting in 1, 2, 3, so far. Next, we traverse the right subtree of node 3, which leads us to node 4. At node 4, we traverse its left subtree first, which is none, so it returns an empty list. We then visit node 4 and add its value. Its right subtree is also none, returning another empty list. Combining these results gives us 4. Finally, combining all the traversal results from the entire tree gives 1, 2, 3, 4. The elements are now sorted. To find the second smallest element, we simply access the element at index k1, which is 1. This gives us the result 2. In this second example, the task is to find the fourth smallest element in a larger binary search tree. Here, the root node is 5, with 3 as its left child and 6 as its right child. Node 3 has 2 children, 2 on the left and 4 on the right, while node 2 has a single left child, which is 1. We begin by calling kth_smallest with the root node 5 and k equals 4. Using an in-order traversal, we start at node 5 and first traverse its left subtree by calling in-order 3. At node 3, we again traverse its left subtree by calling innerter 2. Continuing this process, we reach node 2 and then traverse its left subtree, reaching node 1. Since node 1 has no left child, the traversal returns an empty list. We then visit node 1 and add its value to the result. Traversing its right subtree also yields an empty list, so the combined result at node 1 is 1. Returning to node 2, we now visit it and add its value, resulting in 1, 2 so far. Since node 2 has no right subtree, the result remains 1, 2. At node 3, we now visit it and add its value, combining the results from the left subtree and the current node to get 1, 2, 3. Next, we traverse the right subtree of node 3, which leads to node 4. For node 4, both its left and right subtrees are none, so we simply visit it and add its value, resulting in 4. Combining these results gives 1, 2, 3, 4 for the left subtree of node 5. Returning to node 5, we now visit it and add its value, combining with the left subtree result to get 1, 2, 3, 4, 5. Finally, we traverse the right subtree of node 5, which leads to node 6. At node 6, both its left and right subtrees are none, so we visit it and add its value, resulting in 6. Combining all these results gives the sorted elements as 1, 2, 3, 4, 5, 6. To find the fourth smallest element, we access the element at index k1, which is 3. This gives the result 4. In the third example, we are working with a binary search tree where each node only has a right child. The root node is 1, with 2 as its right child, followed by 3 and then 4. The task is to find the third smallest element in the tree. We start by calling kth smallest with the root node 1 and k equals 3. Using an innerter traversal, we begin at node 1 and traverse its left subtree. Since the left subtree is none, the traversal returns an empty list. We then visit node 1 and add its value to the result. Next, we traverse the right subtree of node 1, which leads to node 2. At node 2, we first traverse its left subtree, which is none, returning an empty list. We then visit node 2 and add its value. Moving to the right subtree of node 2, we reach node 3. At node 3, we again traverse its left subtree, which is none, returning an empty list. We then visit node 3 and add its value. Continuing from node 3, we traverse its right subtree, which leads to node 4. At node 4, both the left and right subtrees are none, so we simply visit it and add its value, resulting in 4 from node 4. Combining the results from node 3's subtrees, we get 3, 4. Going back up to node 2, we combine its left subtree result, which was empty, the value 2, and the right subtree result, 3, 4, to get 2, 3, 4. Returning to node 1, we combine its left subtree result, which was empty, the value 1, and the right subtree result, 2, 3, 4, to get 1, 2, 3, 4. This gives the sorted elements of the tree. To find the third smallest element, we access the element at index k1, which is 2. The result is 3. In this solution, the time complexity is primarily influenced by the innerter traversal of the binary search tree, or BST. Let's break it down step by step. The innerter function is a recursive function that processes each node in the tree exactly once. For each node, it performs 3 operations. It recursively traverses the left subtree, appends the value of the current node to the result, and then recursively traverses the right subtree. Since each node in the tree is visited once, the overall traversal involves n operations where n is the number of nodes in the tree. Additionally, the innerter function combines results from the left subtree, the current node, and the right subtree using the plus operator. When combining 2 lists, the time required depends on the size of the lists being merged, which adds up to n across all nodes in the tree. Therefore, the total time complexity for the traversal and combination is n. Accessing the kth smallest element from the list of sorted elements, achieved by the operation sorted_elements, k1, is extremely efficient with a time complexity of 1, since it directly indexes into the array. Combining this with the traversal time, the overall time complexity of the solution remains n. Now, let's consider the space complexity. The first factor influencing space usage is the recursive call stack. The depth of recursion depends on the height of the BST. In a worst-case scenario where the tree is skewed, this height could be n, leading to a stack size of O, n. In a more balanced tree, the height is approximately log n, resulting in a stack size of O, log n. The second factor is the list used to store the inner traversal result. This list holds all n node values, requiring O, n, space. Therefore, the largest contributor to space usage is the traversal result, making the overall space complexity O, n. Taking both factors into account, the total space complexity in the worst case, where the tree is skewed, is O, n, due to the recursion stack and the list storage. Even in the best case for a balanced tree, the space complexity remains O, n, because the size of the list storing the traversal dominates the stack usage. Now, let's compare this solution to other approaches. A brute force method might involve performing a complete traversal of the BST to generate a sorted array and then indexing into it to find the kth smallest element. This approach would also have a time complexity of O, n, for the traversal and a space complexity of O, n, for the storage. However, an optimized approach could avoid storing all elements by performing an in-place inner traversal, stopping after the kth smallest element is found. This would reduce the space complexity significantly to O, log en in the best case, since you would only need the recursion stack without an additional list. Mathematically, the time complexity of this solution can be explained by the fact that each node in the tree contributes exactly one recursive call and one list concatenation operation. With n nodes in total, the traversal and combination steps add up to a time complexity of O, n. For space, the list that stores all node values requires O, n, space, which dominates over any other space requirements, leading to an overall space complexity of O, n. Let's conclude with an analysis of the best, average, and worst cases. In a balanced tree, the time complexity remains O, n, since every node is visited during the traversal, and the space complexity is dominated by the list storage at O, n, while the recursion stack contributes only O, log, n. In a skew tree, the time complexity is still O, n, but the space complexity is also O, n, due to both the list storage and the deeper recursion stack. This consistency in time and space complexity across cases highlights the efficiency of the solution. When working with this problem, there are a few common mistakes to watch out for. First, it's important not to confuse a binary tree with a binary search tree, or BST. In a BST, the left subtree contains nodes with values smaller than the root, while the right subtree contains nodes with values larger than the root. If you apply generic binary tree traversal techniques without leveraging this property, your solution will likely be inefficient. To fix this, you should use the BST property strategically. For example, performing an inner traversal will give you the nodes in sorted order. Another mistake is traversing the entire tree unnecessarily. If you compute the full inner traversal and store all nodes in an array, you end up wasting both time and space, especially since you only need the kth smallest element. Instead, you can stop the traversal as soon as you encounter the kth element, which is easily achieved by tracking progress with a counter. Lastly, ignoring edge cases is a frequent pitfall. For instance, if the tree is empty or k is out of bounds, your code might crash. To avoid this, always validate inputs and handle edge cases, like null trees or invalid values for k, to ensure robustness in your implementation. Another mistake to avoid is overcomplicating the solution. Some people resort to additional data structures like heaps or arrays, but this can make the code unnecessarily complex. Instead, aim for a minimalistic solution that takes full advantage of the BST properties. Using a simple recursive or iterative inner traversal is often more than sufficient. Additionally, recursion itself can become inefficient if not tailored for this specific task. Writing a standard recursive inner traversal without stopping early can result in extra, unnecessary recursive calls. A better approach is to pass both k and immutable counter into the recursive function, allowing you to exit the recursion as soon as the kth smallest element is found. This early stopping mechanism improves both time and space efficiency. For interviews, it's crucial to understand the optimal approach to solving this problem. Most interviewers expect a solution with a time complexity of O, h plus k, where h is the height of the tree. This is achieved by performing an inner traversal and stopping once the kth smallest element is found. In terms of space complexity, you'll often need to discuss the trade-offs between recursive and iterative implementations. Both approaches use space, but iterative solutions can provide better control over memory usage, which may make them preferable in some scenarios. Additionally, interviewers often ask follow-up questions, such as finding the kth largest element instead of the kth smallest. This can be solved using a reverse inner-order traversal. You might also encounter questions about dynamic trees, which require more advanced techniques like augmenting the tree with node counts to handle updates efficiently. Finally, always bring up edge cases during interviews. Clarify whether k is guaranteed to be valid, and ask whether the tree is balanced or unbalanced, as this can affect the efficiency of your solution. Related problems to study include validating a binary search tree, finding the lowest common ancestor, and working with BST iterators. There are also alternative approaches you might consider, each with its own trade-offs. One such method is the heap-based approach, where you use a max heap to maintain the smallest k elements of the BST. The root of the heap will then be the kth smallest element. However, this method has a time complexity of n log k, which is less efficient for large BSTs, and it requires k space, which can become prohibitive if k is large. Another option is to augment the BST by storing the size of the left subtree at each node. This allows you to compute the kth smallest element in time, but it comes with its own trade-offs. Specifically, maintaining these node counts during tree updates requires extra space and pre-processing, and the implementation can become quite complex. Lastly, there's the Morris traversal, which performs an inner-order traversal without using recursion or a stack. This method is space-efficient, requiring only additional space, but it temporarily modifies the tree's structure, making it challenging to implement. While interesting, Morris traversal is typically not the go-to method in interviews unless explicitly requested. Each of these alternatives has its strengths and weaknesses, so choose the one that best fits the problem constraints and context. Great job! We've successfully solved LeetCode problem number 230, kth smallest element in a BST. We reviewed key techniques like in-order traversal and discussed their time and space complexities. Remember, mastering tree traversal is essential for many coding challenges. Thanks for joining, and don't forget to like and subscribe for more tutorials. Happy coding! That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!